Welcome everybody to my part on this show Q&A. We are going to be focusing on different vulnerabilities analysis, and in particular, we are getting through two report vulnerabilities that were present on different public contests that were held on Code Arena, and maybe we have time. We'll also get into something related with digital signatures and vulnerabilities related with them. So basically, the main purpose of today's workshop here in ShowQA, in my talk, is to let you get into how an attacker thinks. Because when we have a code base, there are two parts here. We have the developer, and then we have the attackers, or the people who is trying to get break into the code and get things work incorrectly. Not only attackers, but in this part we also have security researchers, which should have an attacker mind, or should think like an attacker is going to be thinking and trying to get into the code and break things. Because when we have a developer, if developers can be thinking like a developers or an attackers, the correct and the perfect situation would be thinking as both during the creation of the code bases. Because when you only think as a developer, you are only thinking about or right in the direction that there's only a single and a correct execution of the flow of the code. But when you think as an attacker, you are not only thinking on this direction, but you could be thinking about executing different function in an unexpected way. For example, executing function B before function A, when the expected workflow would be A and then B. So thinking as an attacker would be thinking in a different order. So when you are a developer, you should also be thinking as an attacker, just to protect your code and implement the necessary and sufficient checks to have your code free from vulnerabilities.
Awesome.
And so today we are going to cover, as I mentioned, different vulnerabilities. We are not getting too deep into the whole code bases, but on different points that I want to mention and get you this mind shift and get your brain working as an attacker.
Awesome. Can I ask you to do something, Jose? Can you please make your font a little bit bigger so people that are looking at this at a small monitor they can see it a bit better? Yes, that's perfect, brother. Thank you so much.
This is enough?
Yeah, it's enough. Thank you so much.
Thank you, mate. Okay, perfect. So here we have, as a first example, this code base from Thor Wallet, which was, as I mentioned, a public contest that were held in Code Arena that contained a high severity vulnerability here that we are going to cover today. So we have this smart contract. As I mentioned, we are not getting too in detail about the whole code base or any specific parts, but the part that we want to focus today. But we have this smart contract, which also has different public and private variables and the constructor. We have some getter and setter functions, and here this function, the credit one, is not important for this purpose of today's talk, but we have here the three functions that contain the vulnerability, which is not an direct error on the code. For example, an access restriction that were missed is not this type of error, because thinking as a developer, you could detect an access restriction vulnerability when it is missing. But as I mentioned today, we need to think out of the box if we assume that the box is how a developer thinks. But we have here the transfer function, the transfer from function, and an internal validate transfer function. We can see that the validate transfer function, the internal one, is called before the edit from the parent smart contract for the transfer and transfer from functions. And as you may be thinking right now, of course, this validate transfer function is checking if certain conditions are met or not in order to allow the transaction to be executed or revert it. So we have here the value transfer function. We're going to go through this, and of course we have this part which is where the checks are met. We can see that the transaction is going to revert if the sender is not, well, the front part is not the owner, or it is not coming from an allowed transfer smart contract or to an allowed transfer contract. Also, as well, if the is bridge transfer lock, if is bridge token transfer lock variable is set to true, that should be reverting. And well, we have here some other conditions, but the important one is this one. This means that if this function is set to true, that would mean that there should be not transaction to related to bridge through these tokens. So what happens here? Okay, let me get the whiteboard. Yeah, you should be checking this because I want to explain something. How bridges work. Okay, let me draw something. I really like to draw things to understand concepts. So let's say we have here a user which is holding the bags of tokens, and we have here another user. So basically, the situation is that when we want to transfer the tokens, the transaction could revert, but also at the same time it will have a bridge. So let's imagine that we have a bridge here. Okay, for those who don't know what are bridges, basically, if we want to transfer tokens are deployed within a specific blockchain, and to cover the transfer of tokens to another blockchain, we need a bridge because they cannot be transferred directly through different blockchains. So let's imagine that we have a user here in, for example, let's say Arbitrum. So this first user is having his tokens in Arbitrum, and we have here a second user which is, for example, in let's say, for example, Base network. So okay, let me put this here. So let's say we have the bridge, which is something like, we can think as a bridge as an intermediary, which basically has a smart contract. Let me get this here. We have a smart contract here, and the first user, you might be thinking that it's transferring the tokens through the to a bridge in the Arbitrum network, and the bridge is releasing the tokens in the base network to the second user. This is how the bridge should work, or are working from a high level perspective, but if we get deep into how this specific is working, this is not a transfer of tokens, but instead of that, it's a bar and a mint of tokens. So basically, the bridge is not using the transfer function, because otherwise, if this is set to true, the transfer is going to revert. That would be the expected behavior, and that would be the case where there are no vulnerability here. But the case is that the bridge is using a vuln function, a vuln call, and a mint call. So you are bypassing the transfer of tokens. So basically, you have, let's imagine that you want to transfer your tokens to yourself or another person. Let's say it's user 2 in the same network in Arbitrum, and here you are user 1. You are not going to be able to transfer the tokens directly, because the transaction is going to be reverting, because you are using a simple transfer from, which is calling the internal value transfer. But you can be using a bridge, because the bridge is not going to be using transfer functions, but mint and burn functions. So how would it work? You are basically using, in order to exploit the vulnerability, you are basically executing two operations through the bridge, which means that in order to execute the same operation, transferring tokens from user A, user 1 to user 2, in Arbitrum, you are basically first transferring your tokens to the base network through the bridge, and then you are transferring them back to Arbitrum, but on the second operation, you're pointing to your destination address. So as a result, you will be having your tokens transferred from user 1 to user 2, but without using the transfer from functions, but using a workaround, which is bypassing the check. I think this is, as I mentioned, this is not something direct, like a missing of an asset restriction modifier, but something that should be like thinking out of the box, as I mentioned. So here we can see how the proof of concept were created by the person who reported the vulnerability in the contest. We have here the test case where we have user 1 transfer 10 tokens to user 2 by bridge when the transfer is disabled. So I don't want to get to detail, but we have here the setup for the whole proof of concept to work, and we have here three cuts. This three cuts is directly proving that transferring tokens directly is expecting to revert, and this is what is happening. And then we have here the workaround, as I mentioned, using the bridge, using two-step bridge operations to transfer tokens from user 1 to user 2. Here, well, we have the setup because it is using the layer 0 bridge, and there are certain options and parameters that should be correctly implemented before executing the operation, because this is where the options and the whole parameters are set. And we have here the first operation, which is transferring the tokens through the bridge. And here we have also the creation of the second parameter for the second operation. And we have here the second bridge operation, which are transferring the tokens through to the user 2. And if this is working correctly, this would be checking that the balance before the second transfer on the user 2 address is 0, and then it's going to be 1. So let me execute this, and we'll check the final result if this works correctly. And here we have, let's ignore this console log were for after the first execution of tokens through the first operation, but the important ones are here. We have the second user, the balance for the second user before the operation, which was 0, and after the execution of the operation, which is I don't know the exact number, but larger than 0. This is bypassing the invariant. Invariants. What are invariants? Invariants are conditions or specific rules that should be met and followed through the whole contract or protocol if some conditions are met. For example, the invariant here would be if this variable is set to true, there should not be any transfer of tokens in any way. But as I have played here, we can have a workaround just to not use the transfer and transfer from functions, but use bridge operations. And we have demonstrated that the user 2 is receiving tokens even when it should not receive them. Okay, so that would be the first sample of how you should be thinking as an attacker, not directly into the code, but trying to get workarounds, external things that can be called and execute to get into the code base. So let's go for the second vulnerability, an operation here. Let me get a bigger font so you can font size so you can check it out better. And here we have something really similar. As you mentioned, well, as I mentioned, you could be thinking on this code base on, or on the last one, you could be checking line by line. If what I mean is, when you start an audit, you should get the not only how the lines of code are written, but also how the protocol should work, and get a bigger picture of everything, how everything should be working. Because you could be checking the last smart contract that we have covered, and you could be finding no vulnerabilities and no errors, because there were no errors on the code. When I mean directly on the code, because you follow the workflow that developed, and you don't perform any workarounds like I demonstrated, everything would work correctly. There will not be reverts or anything wrong. But when you think out of the box, you could get a high severity vulnerability, as in this contest were reported. And here we have another protocol. We have LiquidRon, which was also a public contest on Code Arena, where there were a high severity issue. Here we have a larger smart contract, more lines of code, but as I mentioned, we don't want to get too deep into this, but focusing on the key points. So what do we have here? We have here a smart contract which is working like a vault, which is implementing the ERC 4626 standard, and we have several functions here. What are the key points here? Well, basically, the key points on this type of standards, which I think could cover this before, but is how the shares, how the amount of shares are calculated. Because let's get the whiteboard. The key points here, of course, the code base can have different key points, but what I want to focus here is that when you have a user which is when we have a user which is transferring his tokens to the vault, to the smart contract. This is the smart contract or the vault. You will be having the user transferring some tokens and getting some shares back. So the amount of shares is not 100% of the times equal to the amount of tokens. That would not make sense in most of the cases. I mean, you transfer X amount of tokens, you would not be receiving X amount of shares, or maybe you would be. That would depend on the protocol. But what I mean is that that could be Y. Maybe Y could be equals to X if certain conditions are met. That depends on how the protocol were thought. So what is important here is the formula that is used here inside the smart contract of the vault to calculate the amount of how Y is working here. So in this case, what do we have here? Okay, so we have, let me get this audit tag here. We have this total asset, which is also used in several parts of the protocol to calculate the amount of shares. Here we have in the convert to shares function that uses the total asset, the total assets variable, and the total asset function is calculated as the super, the total assets default function from the standard, but it's also adding the get total staked amount, the amount staked which is returned by the get total staked, and we have also the get total rewards. Okay, so you might be thinking, so what's the problem here? Basically, the problem is that this protocol is implementing also this variable, the operator fee amount. What is this? Basically, we have some type of fee which is an amount of tokens that will be transferred to the operator. The operator is like, could be anything. I don't want to get into what is this here, but I want you to have the concept and extrapolate it to your code bases or your future analysis on other audits. So what you should be getting here is that there is an external actor that is getting a fee. So when you have this type of things, you could be having your vault with your user working correctly, and you can have an operator here which is earning X amount of fee. So how the fee is paid to this external actor, okay? So this is the key point, how the fee is paid and how it is calculated. Well, there are two options. If the user is paying X amount of T tokens, the operator could be also getting T tokens or could be getting another token. For example, let's say S tokens. What I want to represent with this S and T is that they are two different tokens. I mean, different addresses. So the amounts are not interconnected if the user is paid T tokens and the operator is getting S tokens. If that was the case, where the operator is getting S tokens, there would be a vulnerability here. But the problem is, or the vulnerability here is that the operator is also getting T tokens. Again, when I mean T tokens, I mean the type of tokens. I don't care about the amount. Why it is important? Because, of course, you should now combine both. Okay, let me get this here. We have the function here, which is calculating the total assets amount, but it's not taking in consideration the amount of tokens that is going to be paid to the operator. So the problem is that the total asset is trying to get the whole amount of assets that are considered within the protocol, even the assets that are going to be paid, the tokens that are going to be paid to the operator. This is obviously a vulnerability here because this amount of tokens should be subtracted from the total amount that is calculated, well, that is used to calculate the conversion from tokens to assets and the other way around, to assets from assets to tokens. Why? Because let's imagine this workflow. I don't want to get here too technical in the formula because you already saw the formula, but I want you to think that the formula is getting the whole amount of assets. So let's take this vulnerability analysis step by step. Let me get this viewer. Okay, let's copy that and let's get that the first step is, let me remove that and let me remove that. Okay, let me get this. Okay, let's imagine that the user is transferring X amount of tokens to the vault and he is expecting to receive he actually receives Y amount of assets. Okay, these are assets, no tokens, assets. Okay, perfect. So if just after this first operation the user wants to get his tokens back by returning the already received assets, the workflow should be the following one. Okay, the user should be transferring Y amount of assets and he is expecting to receive the same amount of tokens that he input before, which is X amount of tokens. As there has not been any other operation between this first step and second step and the total amount of assets is the same, so the formula is going to be working if it is correctly implemented in both ways, from tokens to assets and from assets to tokens. That will be working correctly. But remember that our formula were also considering the amount of tokens that are going to be transferred to the operator just after the amount that is accounted for the operator is also considered to calculate the amount of assets. So this is the expected workflow, but the vulnerability comes here. What happens if here, after the first step, the operator comes and he withdraws the fee that he can withdraw. So basically here, this is the second step right now, and here we have the third step. So what happens here is that the operator is getting set amount of tokens, no assets. So this is correct because the operator should be able to withdraw his fees. But what happens on the third step? So on the third step, the user is trying to convert these shares into the assets into the shares into tokens again, and he's expecting to receive X amount of tokens, the same amount, but now the formula is missing the amount of fee that were paid to the operator. So right now the user is not going to receive the whole expected amount, but less amount than the expected one. So he is going to receive less amount of tokens than expecting. So this is obviously a vulnerability because the operator always, when the accumulated fee is not zero, could be also anytime from running this operation, the third operation, to execute his withdrawal of tokens just after there's a single deposit, and the attacker is going to the user is going to receive less amount of tokens. This can be seen here. As I mentioned, let's see what is this variable. This variable is obviously is a fee variable here, but there is an external function which has no restriction in time, any condition, or any other condition. The operator the fee recipient, which is the operator, can call this function at any time, and if this variable is not zero, then it's going to be put as zero and withdrawn to the operator. And of course, after this execution, the amount of assets that it's accounted for the user is going to be lower. How this can be solved? Well, let's first check the proof of concept. Let me get it here. This is the good one. Okay, let's check how this is implemented so you can have more in detail consideration here. Well, we have of course the setup for this, having this working, but the important part is here. We have we have an assert true, which is checking that the fee for the operator is equal to zero, but after executing a harvest operation, which is something internal from the smart contract, which is the function incrementing the fee for the operator, we are now checking again if the fee of the operator is greater than zero, which is the case. And now we have the check of the vulnerability. We have the user which is depositing some tokens on some ether, and we are checking the balance, and which is the expected redeem amount if he's transferring the tokens back again. And then we have here the operator, which is claiming the fee, and now we are checking that the fee is equal to 0 again. So that part is obviously representing the first step. This part, which is the operator claiming the fee, is representing our second step in the diagram, and the last part here, which is the user redeeming the tokens back, is representing it is actually this third step. So we have two different console logs here, and we have this assert true. This assert true is basically checking if the user balance should be equal the same as the expected redeem amount. Let's remember that this redeem amount was calculated before the operator claimed the fee. So if the vulnerability is present, this assert true should fail. So let's transfer this. Let's execute this proof of concept, and we expect this test to fail, not to work correctly, because the balance is not going to be the same. So let's check this, and let's see what's the result. Here we have, as I mentioned, the test is failing because we have here the console logs where we have the balance and the expected amount, which is not the same. So how can we solve this? Okay, so what you might be thinking right now, because of the things that I mentioned through the code base analysis, here within the formula should not be taking the amount of expected assets or tokens for the operator to be accounted for the calculation of assets or redeem amount for the user. So this is really simple to fix. We should now just include this operator fee amount as a fraction of the total assets, which is considered to be taken in consideration for the calculation. So let's execute the test again, and let's see what's the result. There is nothing wrong. The test should be working right now correctly and passing without errors. And there we go. Here we have the test passing. We have the console logs that is basically saying that the balance of the user after the execution of the operation is the same one as the expected one. So the user now can redeem his assets even when the operator has claimed the fee on the second step, and that will be the second analysis of the second code base for this workshop. And just before finishing, I want to mention something about signatures as well. This has been more in detail in a workshop that is going to be published by Sokyo. You can also check that the whole code base on GitHub, which is going to be published also by our team. But here you have the whole code base. But yeah, just before finish, let's cover one more issue, which is going to be about signature-related attacks. So basically, what happens here? Signature is normally one of the things that I consider more complex by junior or even senior smart contract security researchers. And one of the things that in this workshop, when the team is going to publish this one, you will get a lot of vulnerabilities that we cover there. But I want to focus today only just on how the easy recover default function from Solidity is working. Basically, what happens here with signatures just to give you a more in detail context on this. You can use, well, a user can have two options: can transfer and execute a transaction directly on the blockchain by executing a function through a smart contract, or can sign a message off-chain, which can be later introduced on-chain by himself or by another party. So when there is a signature of a message, we have the signed message. We can get who is the signer of the message on-chain, just to validate the who was the signer and if the signer is valid or not. How can we do that? We can do this on different ways. Solidity has the default function easy recover, which has the hash, which has as an parameter the hash, and also the V, R, and S parameter from the signature. But what is the vulnerability here? I've seen this on many code bases where there is correct validations on, for example, replay attacks, where here we can see that there is a mapping called use hashes, which is basically marking here that the hash is already used, just to avoid anyone using the hash twice. I mean, you see a transaction on the mempool, or even later when a hash has been used, this is public. You could be getting the same hash and introducing this again on the function. So this is why we have this replay attack mapping. Well, this mapping to avoid replay attacks. But normally when there are a lot of code bases that are validating a lot of things around signatures, but they are missing one of the key points here, and it's if the signature is valid or not, because otherwise you could be bypassing the check. And what do I mean by that? Was basically this thing here. You should be checking if the signer is different from address 0, because otherwise you could be implementing any checks, but not the most simple one, which is checking if the signature is valid, because you could be introducing any parameters which will make the easy recover return an address 0 from the execution of the function. So this is something really important to check in code federation, and that's something I wanted to mention before finishing the workshop. And that would be the 3 analyses of vulnerabilities that has been covered by me on this talk through the Tokyo Day.
Bro, that's really, really good talk. Thank you so much. Very insightful. I mean, I can see that we're going to create a bunch of content out of this, and it's going to be really good for the community.